Hello, and welcome to Linear Algebra. This is Lecture 16, Bases and Linear Maps. So last time, we talked about bases, right? I'll be reviewing the definition in a second, but this is a linearly independent spanning set. This time, we want to talk about how using bases, we can understand linear maps. So the relation linear maps. Okay, so let's start by recalling definition. So recall that a set, which we're going to take as being ordered, so we'll call it a list, and I'll denote it with round parentheses, is a basis of a vector space V. This means two things. First, that the span of this list is all of the vector space, and two, that this list is linearly independent. Okay, so one of the things we saw last time is that you can rephrase this as saying every vector in the vector space can be written in one and only one way as a linear combination of vectors in B. Okay, so directly from the definition, it is easy to see that a linear map acting between the vector spaces V and W is determined by what it does to a basis. And in fact, something stronger than that is true. Here's the theorem. So suppose you have a V1 through Vn is a basis for V. And W1 through Wn is any list of n vectors in W. Then there is a unique map, linear map between V and W, such that T of Vi is equal to Wi for all I. Okay, so this is stronger because this says that not only do I know the map entirely by knowing what it does to a basis, but it also says that if you pick any list of vectors in W, there is a linear map that sends these vectors to these vectors. And by saying that it sends this list to this list, I mean that it sends the ith vector to the ith vector. Okay, great, so let's do the proof. Okay, so since this is a theorem that's coming right after the definition, it's really only going to use the definition. So first, let's show that there is such a map. Okay, so I know what it's going to do to all of the elements of the basis. I need to tell you what it's going to do to an arbitrary vector in V. So given an arbitrary vector, let's call it U. we can write it in one and only one way, as a linear combination of the vectors in our basis. So let's say that the coefficients are going to be A1, V1. So the coefficients are AIs, so that U is equal to A1, V1 plus dot, dot, dot up to AN, VN. And let's define T of U, right? I have to give you a vector in W to be. So what I'm going to do is I'm just going to take these coefficients, these same coefficients, but now I'm going to use them to write a linear combination of the W's. Okay, and that's our definition of the linear map T, right? So to repeat, the definition of the map T says you give me a vector U, I take this U and I write it as a linear combination of the vectors VI, and then I take those coefficients, right, which are uniquely determined by U, and I use them to write a linear combination of the vectors WI, and that's what I call T of U. Okay, so let's check that this does what we needed to do. So clearly, T of VI is equal to WI for every I. So we just need to check that it's linear. Okay, so how do we check that it's linear? Well, remember that a linear map is a map that satisfies two things, additivity and homogeneity. So it takes vector sums to vector sums, and it takes scalar products to scalar products. You can check those at the same time, as we've seen, by seeing that you take linear combinations to linear combinations. And it's enough to check for linear combinations where you have two vectors in the vector space and one scalar. Let's call it C. So given these, we need to show that T of U1 plus CU2 is equal to T of U1 plus CT of U2. Okay, now our recipe for T says that I should take each of these vectors and write them as linear combinations of vectors in the basis for V, and that'll tell me how to write the image in terms of W's, right? So here, notice that if U1 is equal to the sum of, say, AJ, VJ, so sum J goes from 1 to N, and U2 is a sum of BJ, VJ, J goes from 1 to N, then U1 plus CU2 is equal to the sum, J goes from 1 to N, of AJ plus CBJ, VJ. Right? And this, because it is a linear combination of the vectors in the basis, there is only one way of writing this as a linear combination of the vectors in the basis, so this has to be it. And so T of U1 plus CU2 is equal to sum J goes from 1 to N. I take the same coefficients, but I replace the VJ with the WJ, right? That's our definition of T. And now here, I'm just going to use that this is a linear combination to write it as a sum of vectors where I just use the A's plus C times the sum of the vectors where I just use the B's. And then we recognize that as T of U1 plus C times T of U2, and that is what we wanted to show. Right, let's put a check mark. So that takes care of one direction. We have now shown that there is such a map. Next, I want to show that there is only one such map. Right. So secondly, we need to check that this is the only such map among linear maps. Okay, so assume the way we show that there's only one is we assume we have two of them and we show that they're actually the same. So assume that S is a linear map from V to W. And it satisfies that S of Vj is equal to Wj for all j. Then, for any U and V, let's say that U is with, let's say it's the same notation as before, so it's just AJ, VJ. Then we have, so S of U is equal to S of this linear combination but because S is linear, I can pull out the sum and the scalar products, scalar multiples, and write it like this in terms of the S of Vj, but I know what the S of the Vj are. Those are the Wj's. And then I recognize what I ended up with, this linear combination of the Wj's as T of U. And that proves the second direction, that there is only one. Okay, there we go. So this construction gets used all the time. If you want to define a linear map, you really only need to say what you're going to do to a basis. And then there's only one linear map, so you can just say, take that linear map. Since it gets used all the time, there is a shorthand. So the shorthand for this construction is to say, we specify T of Vj is equal to Wj, and then extend by linearity. Right? So this extend by linearity just says, okay, once I've told you what to do to the Vj's, since I want it to be a linear map, I've also told you what to do to any linear combination of the Vj's. Right, so we say that you just extend it by linearity. In particular, one way of showing that two linear maps S and T, so I need them to be going between the same spaces, of course, so linear maps between V and W. One way of showing that they're the same is to find a basis of V such that S and T act the same way on each basis vector. Okay, so then by the theorem, since there's only one linear map that acts in a given way on a basis, these maps have to be the same. Okay, now this extends a little further. Not only is the map, or let's say because the map is determined by what it does to a basis, if I want to check if a map has certain properties, I should be able to decide that just by seeing what it does to a basis. So here's an example of what I mean. Let's say you have a linear map between vector spaces V and W. And let's say you have a basis V1 through Vn of V. Okay, then T is an isomorphism. Right, so remember, an isomorphism is an invertible linear map. If and only if the image of this basis, so T of V1 up to T of Vn, is a basis of W. Okay, so an isomorphism is exactly those linear maps. Isomorphisms are exactly those linear maps that send bases of V to bases of W. And you only need to check for one basis. Then it's automatic that it does it for any other basis. Okay, so let's prove this. It's an if and only if, which means we need to prove two directions. We need to prove that if you assume this, then this is true, and vice versa. If you assume this, then this is true. Okay, so let's start with this direction. We get to assume that T is an isomorphism. We want to show that T of V1 through T of Vn is a basis of W. Okay, now remember from the beginning of class, what we want to show to see that this is a basis, so we want to show that it spans and that it's linearly independent. Okay, so let's show those one at a time, starting with span. So let's show that the span of the set is all of W. Okay, how do we show that the span is all of W? We pick an arbitrary vector in W, and we show that we can write it in terms of these. Okay, so given a vector lowercase w inside uppercase W, since T is an isomorphism, there is a vector V in V such that T of lowercase v is lowercase w. Now, since V1 through Vn is a basis of V, right? That's an assumption. It's something we're given. We can write actually, let me call it U, just so I don't have as many V's. So given lowercase w, there is a lowercase u such that T of u is equal to W. And then because this is a basis, I can write lowercase u as a linear combination of the VJs for some coefficients AJ in the field. Some coefficients, let's write like this. A1 through AN in the field. Hence, the vector W, which is T of U, is equal to T of this linear combination of the VJs. But then because T is a linear map, I can write this as the linear combination of the T of VJs, right? But notice, I started with an arbitrary vector in W, and I have now written it as a linear combination of the T of VJs. That means that the T of VJs span all of W. Okay, so that takes care of that. The second part of the definition, let's show that this set T of V1 through T of Vn is linearly independent. Okay, now, basically every proof of linear independence starts the exact same way, right? To prove linear independence, you take a linear combination of these elements equal to 0, and then you have to show that the coefficients have to be 0. Okay? So every proof starts the same way. You would say, let this linear combination, let's call these CJs of T of Vj. Let this be 0 for some C1 through Cn in F. We need to show that Cj is equal to 0 for every j. Okay, every proof of linear independence starts the same way. Okay, in this case, let's say indeed, if you have that this linear combination is equal to the 0 vector, then we have that the 0 vector is equal to, so what I want to do is use the fact that T is linear to rewrite this linear combination as T of the linear combination of these vectors. But T is an isomorphism. So in particular, T is injective. So these together tell us that this vector, right, T is injective. That means that the only way T of something is equal to 0 is if that something is itself equal to 0, right? T of 0 is 0, T is injective, so the only thing that T sends to 0 is 0. So from here I can conclude that this vector, this linear combination of the VJs, is the vector 0. Right, this is the 0 in V, whereas this was the 0 in W, but that's fine. Okay. But since the VJs form a basis, then we know that the set of vectors V1 through Vn is linearly independent. So this equality implies that the CJs are equal to 0 for every j, and you note that's exactly what we wanted to show. Right? So that proves that, and that finishes that direction. We've now shown that if T is an isomorphism, it sends a basis to a basis. Okay, now we want to prove the other direction. Right, so assume that T sends a basis to a basis, sends this particular basis to a basis. We need to show that T is an isomorphism. Okay, so an isomorphism is an invertible linear map. Right? We already know that T is linear, so we need to establish that it is invertible. So just like the other direction, we have two things we want to prove. Let's start by showing that T is injective. Okay, so we know that because it's a linear map, being injective is the same as having the kernel be just a 0 vector, right? So injectivity says that if you have two different vectors, they get sent to two different vectors. If we just look at 0, then we want to say that if you have a vector that's not equal to 0, it gets sent to something that's not equal to 0, right? And by linearity, it turns out that if that's the case, then it's true for all pairs of vectors, that if you have two different vectors, they get sent to two different vectors, right? So for linear maps, injectivity, you just need to check the null space. So let's say that we have a vector in the null space. We need to show that it's equal to 0. Okay. Let's write U in terms of the basis v1 through vn. Right? We get U is equal to the sum, j goes from 1 to n, aj, vj. Then U being in the kernel of T tells us that 0 is what you get as the image of U under T. But on the other hand, I can write U as this linear combination of the VJs. And then because T is linear, I can write this as a linear combination of the T of VJs. Okay, but now we're assuming that the T of VJs form a basis. So in particular, linear independence of the set T of V1 through T of Vn implies that all of these coefficients are equal to 0, right? If you have 0 as a linear combination of the T of Vj's, and you know the T of Vj's are linearly independent, then you know that all of the coefficients of that linear combination are equal to 0. So U is the vector 0, right? Just by plugging in right there. If you know all of the coefficients are equal to 0, then this linear combination is itself the vector 0, right? And that's exactly what we needed to show. So we're done with that. Finally, we need to show that T is surjective. Okay, so now we want to show that the range is everything. So given a vector in W, we need to show that W is T of U for some U in V. Okay, right, but what are we assuming? We're assuming that the T of Vj's form a basis. So you give me a vector in W, I can write it in terms of this basis. So writing W in terms of this basis, let's say sum j goes from 1 to n. Let's use Bj for the coefficients. It's Bj T of Vj. Writing it like that, we see that the sum j goes from 1 to n of, no, sorry, the T of the sum Bj Vj is equal to W. So W is equal to T of U with U, this vector sum j goes from 1 to n of Bj Vj. And that's what we wanted to prove, and that's it. That finishes this proof of the theorem. We've shown both implications, right? So let me just recall what we've just shown is that you can recognize whether or not a linear map is an isomorphism by checking what it does to a basis. A linear map is an isomorphism if and only if the image of a basis is a basis. Okay, now if you stare carefully at the proof, you can see that actually we proved two different sub-theorems, if you like. Right, so a basis has two parts. It should be linearly independent, it should span, And to be an isomorphism, there are two parts. It should be injective and it should be surjective. So I'll let you check, and I'll let you formulate and check that the two subtheorems where you only assume one of those properties for T and you get one of those properties for this set also is true with the same proof, no modification. Okay. Now, let's say that I have the same vector space and I have two different bases, right? You probably already know that two different bases of the same vector space have to have the same number of elements, right? Well, it follows from what we've shown so far. So let's write this down. Let's write a lemma from which this will follow. So suppose I have a bunch of vectors inside a vector space V. And these are such that V is inside the span of V1 through Vm. And that the set W1 through Wn is linearly independent. Then M is greater than or equal to N. Okay, so this says, look at a bunch of vectors inside the same vector space. If a subset is linearly independent and another subset spans, then you have to have at least as many vectors in the spanning set as you had in the linearly independent set. Okay. So why is that true? Well, let's use what we know about these sets, right? So we know that this set spans. So that means that every vector, actually, let me strengthen this, it's an equal because I already said that those are inside. Okay. I know that I can write any vector in V as a linear combination of these vectors. And here I have some vectors that are in V. So let's go ahead and write those. So for each j between 1 and n, there are scalars. In the field such that Wj is equal to the sum Aij Vi. Right, so the Vi span, so I can write the Wj's in terms of that. Okay, now let's let A be the matrix whose entries are these numbers, these Aij's. So here, I goes from 1 to m, and j goes from 1 to n. And let's consider the homogeneous system Ax equal to 0. Okay, let's figure out how many solutions does this equation have. If x is a solution, say x has entries x1 through xn, then the sum j goes from 1 to n of Aij xj is equal to 0 for all I. Right, that's what it means to solve this system. And so I can write the 0 vector as the sum I goes from 1 to m of the sum j goes from 1 to n of aij xj vi. Right? Because this is a linear combination of these vectors, but all of the coefficients are equal to 0. Okay, but if I change the order of the sum here, first do the sum over j, and then do the sum over I, then I end up with the sum j goes from 1 to n of xj wj. Okay, but my assumption on the wj's is that they're linearly independent. So if you have a linear combination that's equal to 0, you can conclude that all of the coefficients are equal to 0. Okay. So what we've shown is that the kernel of this matrix is just a 0 vector. Okay, so now let's think about that. If this has a unique solution, that means that you don't have any free variables, right? If you were to form the augmented matrix, take it to reduced row echelon form, knowing that you have a unique solution tells you that you don't have any free variables, which is the same as saying that every column has a pivot. Every column without the augmenting, every column in the reduced row echelon form of A has a pivot. But now since each row can have at most one pivot, you know that, so the number of rows of A is at least as big as the number of columns of A. That is, say, M is greater than or equal to N, which we wanted to show. Okay, so as I mentioned before stating the lemma, it follows that if V1 through Vm and W1 through Wn are both bases of V, then, okay, so we're just going to play them off against each other using this, right? So because the V's form a basis, we know that they span. And because the W's form a basis, we know that they're linearly independent. So that tells us that M is greater than or equal to N, right? But notice that over here, if we have bases, then they can switch roles, right? So we also know that the W's span, and we know that the V's are linearly independent. So using this lemma, we would conclude that N is greater than or equal to M. And putting those together, we get that N is equal to M. Okay, so we call this number the dimension of V. And we say that V is n-dimensional. Okay, if V is just a 0 vector, we say that the dimension of V is 0, okay, and if V is not finite dimensional, we say that it is infinite dimensional. We've seen that before, but it seemed like a good place to repeat it. Okay, excellent. So next, I'll just give you a bit of historical context about this. So feel free to stop listening now. In this case, I want to tell you about who came up with the abstract idea of a vector space. So of course, people started working in Rn, whether they phrase it like that or not, way back when geometry gets started. So certainly the ancient Greeks were working with R2 and R3. In fact, I've heard it say that one reason why the Greeks didn't develop algebra was because they thought of everything in terms of geometry. So like multiplying two numbers, that makes good sense because it's like finding the area of a rectangle. Multiplying three numbers makes good sense because it's like finding the volume of a parallelepiped. But when you're multiplying four numbers, you're finding the volume of something four-dimensional, and the Greeks just thought in terms of what they could see, what they could draw, three-dimensional, and so they just didn't want to think about that. Instead, they'd rather draw figures. I don't know if that's true, but that's one of the things I've heard. So the person who really started working on abstract vector spaces is Hermann Grassmann. He lived from 1809 to 1877. Now, as you know, during the 19th century, the map of Europe was very unstable in terms of political geography. So he was born in a town called Stettin in a country named Prussia. He died in the same town, but now the country was called Germany. And today, that town is not in what's now called Germany, it's in Poland. Grassmann is famous as an example of a scientist, a mathematician, whose ideas were ahead of their time. So he came up with vector spaces and bases and dimension and very similar notions. He came up with linear independence, and he had proofs that were very similar to the ones we went over today. Let's say 1830s, but first wrote it all down 1844. But the thing was, he couldn't convince other people that he was right or that it was interesting. He seems to have been very bad at explaining his ideas. He sort of thought that his ideas were so obviously important that other people should understand that and should make the effort to understand them. He was never able to get a university position. He spent all of his teaching career teaching in high school. And although he did end up being well known in scientific circles, it wasn't for his work in math. It was for his work in languages, which he did when he wasn't able to get recognition for his math work. He studied ancient German and Sanskrit and compared them. And that's how he became well known. So the idea of a vector space and bases and things like this, the way we talk about them now, come from a later mathematician known as Giuseppe Peano, who was alive from 1858 to 1932. Also a turbulent time geographically. He was born in the Kingdom of Sardinia, but he died in Italy. So Peano is famous for his work in logic, especially symbolic logic. So things like the union of two sets and the intersection of two sets, our notation for it come from Peano. Also, he came up with axiomatizations of things that people used a lot. So for example, the natural numbers, the way we work with them today are axioms that he wrote down, right? So this is where you have a set that contains 1, and if it contains an j, it also contains j plus 1. And that gets you the natural numbers. That's Peano. He worked out symbolic logic, and this allowed him to think about theorems very clearly, apparently much more so than his contemporaries. So he became well known for finding errors in statements that other people were claiming to have proven. So he would come up with counterexamples to what they were actually claiming, right? So, it's not that their proof was necessarily wrong, it's just that the proof did not prove what they were claiming. And that, because of sloppy thinking, because they weren't writing things down clearly, they didn't have his notation, his concepts for clarity. He did important work in analysis, and as far as our class goes, he's the one who wrote down the definition of a vector space, very much like the modern definition, what we've been studying in this class. He wrote down what it means to have a basis, to be finite dimensional, and so on. And but his work in analysis I mentioned because he proved something really cool, something very different to what we've been talking about today. So today, we've talked about the dimension and how a space just has some dimension. It's just the number of elements in a spanning set, and it doesn't matter which, in a linearly independent spanning set, it doesn't matter which basis you use, you'll have the same number of elements. So a space is either one-dimensional or two-dimensional, for example. But one thing Peano proved was that that's not true if you're looking at continuous maps that are not necessarily linear, right? If you just look at continuous maps, then he was able to show that there is a continuous map from the unit interval to the unit square that is surjective, right? So it was known abstractly that you could get non-continuous maps that are actually a bijection, and you cannot do a bijection continuously. But Peano was able to show, and this is now called a space-filling curve. It's an early example for fractal, but it's a continuous curve. It's defined on a one-dimensional interval, and it fills up a two-dimensional square. So that's really one of the most remarkable results in set theory. And it shows how the very special nature of linear maps, or if you like, the very wild sort of things you can find among general continuous maps. Okay, very good. So we'll stop there and pick it up from there next time.